Welcome back. In this video, we're breaking down IP addressing and subnetting step by step so it actually makes sense. Whether you're studying for CCNA or just want a solid networking foundation, you're in the right place. Let's get straight into it. The internet is a constantly growing global network made up of billions of connected devices. For these devices to communicate, each must have a unique identifier known as an Internet Protocol address. IP addresses allow data to be sent and received accurately between devices, much like postal addresses enable mail delivery in the real world. In this chapter, you will explore both IPv4 and IPv6 addressing, understand how IP addresses are assigned and managed globally, and learn how subnetting helps organize and optimize networks. You will also gain hands-on experience configuring IP addresses and testing connectivity. So the topics covered are the need for IP addressing, characteristics of IPv4, IPv4 address classes, special IPv4 addresses, subnet masks and subnetting, IPv6, configuring IPv6 on a Cisco device and a Windows computer, then testing end-to-end connectivity. Just as homes and businesses require postal addresses, devices on a network need IP addresses to communicate. These addresses uniquely identify devices and ensure data reaches the correct destination. The allocation and management of IP addresses are handled by the Internet Assigned Number Authority, IANA, operating under ICANN. IPv4, introduced in 1983, remains widely used today, especially in private and home networks. IPv4 addresses are divided into public and private addresses. Public IP addresses must be globally unique and used on the internet, while private IP addresses are used within internal networks. IANA delegates IP address blocks to regional internet registries, which then allocate them to internet service providers, ISPs. The 5 RIRs are Africa, Asia Pacific, North America and parts of the Caribbean, Latin America and parts of the Caribbean, Europe, the Middle East, and Central Asia. ISPs operate as autonomous systems, each identified by a unique autonomous system number. Autonomous systems exchange routing information using Border Gateway Protocol, allowing the internet to function as a connected global network. As more devices and networks join, the internet continues to expand, supported by global infrastructure such as terrestrial and submarine cables. With this global context established, the chapter moves on to a deeper examination of IPv4 addressing, followed by subnetting and IPv6. Although users interact with computers through graphical interfaces, all data is processed internally in binary form, ones and zeros. Whether data is stored on a disk, displayed on a screen, or transmitted across a network, it is ultimately represented and interpreted as electrical signals. In networking, a high voltage typically represents a 1 and a low voltage represents a 0. Just like all data in computing, IP addresses are stored and processed in binary, even though humans usually write them in decimal format for readability. An IPv4 address is 32 bits long, made up of 4 octets. Each octet contains 8 bits. The octets are separated by dots, and a total size 8 bits times 4 equals 32 bits. Here's an example. We typically represent this in decimal, so we would read it as 192.168.1.129. Understanding IP addressing and subnetting is essential in networking. Incorrect IP or subnet mask configuration will result in loss of connectivity. To effectively troubleshoot networks, it is important to understand the fields within an IPv4 packet. Each field plays a specific role in packet delivery. So here we have the key IPv4 header fields. So you got version 4 bits, IPv4 or IPv6. IHL 4 bits indicates the length of the IPv4 header. Differentiated services 8 bits, used for QoS. The total length 16 bits, maximum packet size of 65,535 bytes. You got identification used for packet fragmentation, flags 3 bits, controls fragmentation behavior, fragment offset 13 bits, identifies fragment position, TTL 8 bits, limits packet lifespan, decremented by each router. You got protocol 8 bits, identifies the upper layer protocol, TCP, UDP, and ICMP. You got the header checksum 16 bits, verifies header integrity, source IP address 32 bits, sender's IPv4 address, and destination IP address 32 bits, receiver's IPv4 address. And you got options 0 to 40 bytes, optional routing and control features. If a packet's TTL reaches 0, the packet is discarded. This behavior is commonly observed when sending ICMP packets with low TTL values. IPv4 addresses are converted 1 octet at a time, not all 32 bits at once. Each bit position in an octet represents a power of 2. So you have the bit and the value. So 128, 64, 32, 16, 8, 4, 2, 1. So here's an example of that. An octet where all bits are set to 1 equals 255. That's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. This is why each octet ranges from 0 to 255. To convert decimal to binary, work 1 octet at a time. Subtract values starting from 128 down to 1. If subtraction is possible, write 1. If not, write 0. Here's an example. So you got an example of 172, which is 10101100, 19 000100011, 43 001010011, 67 01000011, and the final binary result is 172.19.43.67, and that equals that. Binary conversion is a core CCNA skill, especially for subnetting. So here we have the IPv4 transmission types. So you have unicast, one-to-one. Communication between a single sender and a single receiver. So you would have a PC to printer or a PC to server. Multicast is one-to-many. Communication to a selected group of devices. IPv4 multicast range 224.0.0.0. Communication to a selected group of devices. IPv4 multicast range and use protocols such as OSPF. Now broadcast, one to all. Communication sent to all devices on the local network. Uses MAC address, but excessive broadcasts can cause broadcast storms. So here's an example of a Cisco IOS broadcast storm control. If the threshold is exceeded, the interface enters a ERR disabled state. Anycast is one to closest transmission method used in IPv6. Multiple servers share the same IPv6 address, and traffic is routed to the nearest server. Here's an example. This address exists on multiple servers globally, allowing users to connect to the closest instance automatically. So here's a summary. IPv4 addresses are 32-bit binary values. Understanding binary conversion is critical for subnetting. IPv4 supports unicast, multicast, and broadcast. IPv6 introduces anycast. Proper IP addressing and packet knowledge are essential for troubleshooting. IANA oversees the global IPv4 address space and delegates large blocks to regional internet registries, which then allocate them via ISPs for public internet use. Some ranges are reserved for private internal networks. IPv4 is commonly discussed in two address spaces: public IPv4 address space, this is routable on the internet; private IPv4 address space, internal use only, not routable on the internet. Historically, IPv4 was divided into 5 classes. In the public space, Class A, B, and C are used for host addressing. Class D is multicast. Class E is experimental. So here we have the IPv4 classes and ranges. Class A for large networks, Class B, medium networks, Class C, small networks, Class D, multicast only, Class E, experimental, reserved.
Public IPv4 addresses must be globally unique and are typically assigned by an ISP. Businesses often configure the public IP on a router, firewall, WAN interface, along with the ISP-provided default gateway. Home users usually receive a modem router that obtains and applies these settings automatically. Because public IPv4 addresses are limited, internal networks use private IPv4 ranges defined by RFC 1918. Private addresses are not routable on the public internet, and ISPs commonly filter them at their edge. Internal devices access the internet using network address translation on the router firewall, which translates private internal addresses into a public address. Certain IPv4 addresses are reserved for specific purposes and cannot be used as standard host addresses. The most common are Loopback, Testnet, and Link Local. Loopback addresses are built into the TCP/IP protocol suite and allow a device to communicate with itself. They are commonly used to test the local TCP/IP stack without requiring network connectivity. So the range is 127.0.0.0/8. Commonly used is 127.0.0.1, verifying that TCP/IP is functioning correctly on a host. Any address within the 127.0.0.0/8 range loops traffic back to the local device. The testnet range is reserved strictly for documentation, examples, and training. Here's the range, defined by RFC 3330. Use case, educational material, vendor documentation, and lab examples. These addresses must never be used on live networks or the internet. Normally, devices obtain IP settings from a DHCP server. If no DHCP server is available, the device automatically assigns itself a link local address using automatic private IP addressing. Here's the range. You have the usable range and the purpose. APIPA enables basic local connectivity but does not provide internet access. An IP address is incomplete without a subnet mask. The subnet mask defines how much of the IP address identifies the network and how much identifies the host. IPv4 subnet masks are 32 bits. IPv6 subnet masks are 1 to 8 bits. And these are used for identify network and host portions of an IP address, calculate usable hosts and subnets, and determine whether traffic should be sent locally or to the default gateway. Historically, IPv4 classes had default subnet masks: Class A, Class B, and Class C. Here's a few examples. In modern networks, custom subnet masks are commonly used, which is covered in the subnetting section. A network prefix is a simplified way of representing a subnet mask using CIDR notation. How it works? Subnet masks are written as continuous ones followed by zeros in binary. Prefix length equals the number of ones. So here's a custom subnet mask example. So you have your subnet mask, the binary, number of ones, network prefix. And the result of that notation is 192.1.2.3/19. Two devices must share the same network ID to communicate directly. The network ID identifies the logical network, similar to a neighborhood address. Devices with different network IDs are on different logical networks, even if physically connected. The network ID is calculated by performing a bitwise AND between the IP address and subnet mask. Here's the AND rules and an example outcome. You got your PC network ID and the router network ID. Although both devices are physically connected, they are on different logical networks and cannot communicate. The solution to this: assign both devices IP addresses from the same subnet. So here's a quick summary. We had Loopback, Testnet, and Link Local addresses serve special purposes. Subnet masks define network and host boundaries. CIDR notation simplifies subnet representation. Network IDs determine logical connectivity. Incorrect IP or subnet configuration results in no communication. This foundation leads directly into subnetting and VLSM, which builds on these concepts. Subnetting can feel intimidating at first. but it's a core skill for CCNA and real-world networking. Subnetting is the process of breaking one IP network into multiple smaller networks, subnets, to reduce IP address waste, create smaller broadcast domains for better performance and fewer broadcast storms, and create smaller broadcast domains. Assume a company has 6 networks, each needing 50 hosts. If you assign a full class C-24 to each network, it works, but it wastes addresses. A -24 has 256 addresses, usable hosts 254. Network ID and broadcast cannot be assigned. If each network only needs 50 hosts, you waste roughly 204 IPs per network. Subnetting solves this by sizing subnets closer to what you actually need. So here is a subnetting design scenario. Company X needs 7 networks. HQ LAN 28 hosts. Branch A 26, Branch B 25, Branch C 15, Wide Area Network 1 2 hosts, WAN 2 2 hosts, and WAN 3 2 hosts. A Class C-24 is appropriate because Class A and B would waste far too many addresses. Step 1. Choose how many subnets you need. Start with network. To create more subnets, you borrow host bits to become subnet bits. So here's a formula, number of subnets equals 2, and then you could try borrowing 2 bits, 2 equals 4 subnets, not enough, 3 bits, 3 equals 8 subnets, enough for 7 networks, 1 spare. So your new prefix would be -24 plus 3 equals -27. New subnet mask would be 255, 255, 255, 224, and that would be -27. Host per -27, host bits left 5, total 2, 5 equals 32. Usable 32 minus 2 equals 30 usable hosts. Step 2. List -27 subnets. Increment equals total addresses per subnet. Subnet 32. So here's a list of the -27 networks. Step 3. Assign -27 subnets to the LANs. Use the first 4 subnets for the LANs. Each -27 gives you up to 30 usable hosts. Each WAN link needs 2 IPs, but a -27 provides 30 usable, so most addresses are wasted. That's where VLSM comes in. Step 4. VLSM for WAN links using -30. Take the spare subnet 192.168.1.224-27, subnet it further into -30 networks, so -30 mask 255.255.255.252. Total addresses would be 4, usable hosts 4, take away 2 equals 2. Increment for -30 equals 4. So inside 192.168.1.224-27, the -30 subnets start 192.168.1.224-30, usable.255, and this continues in increments of 4. Then you would assign the WAN 1, 2, and 3. Remaining -30s are reserved for future WAN links. So key takeaways. Subnetting splits a network into smaller networks to reduce waste and broadcast traffic. Borrowing host bits create more subnets. Leaving enough host bits supports required hosts. -27 works well for 30 host LANs. -30 is ideal for point-to-point WAN links. VLSM lets you subnet subnets to fit different network sizes efficiently. IPv4's public address space is limited. With the growth of smartphones, IoT devices, and cloud services, public IPv4 blocks were depleted in many regions, driving adoption of IPv6, which provides a vastly larger address space. So IPv6 address basics, length 1 to 8 bits, and this is in the format of hexadecimal 0 to 9, A to F, structure 8 octets, each 16 bits separated by colons. So here's IPv6 shortening rules. Drop leading zeros in any hextet. Replace one continuous run of 2 or more 000 hextets with colon. Only once per address. You got your IPv6 prefix length, typical default IPv6 subnet is -64. First 64 bits equals prefix, last 64 bits equals interface ID. IPv4 only devices can't natively communicate with IPv6 only devices, so networks commonly use dual stack, NAT64 and tunneling. So you got your IPv6 packet header fields, version, traffic class, flow label, payload length, next header, hop limit, source IPv6 address, destination IPv6 address. So here are the different IPv6 addresses. You got global unicast, which is public routable IPv6. You got loopback, link local, unique local, anycast, multicast, and modified EUI64. With SLAAC, the router advertises the 64 prefix, and the host builds the interface ID. In modified EUI64, the host splits the MAC into two halves, inserts FFE in the middle, and flips the UL bit. So this is a Cisco note. To enable IPv6 routing on Cisco devices, you'd use IPv6 unicast-routing. You've just taken another solid step toward mastering networking. If you found this useful, make sure to like, subscribe, and share it with anyone else studying CCNA. More labs and breakdowns are coming soon here on Cyber Ed. Stay consistent, stay curious, and I'll see you in the next chapter. Peace.